the end of chapter 13. Does anybody have questions from homeworks or anything that we want to address before we get started on the new stuff for today? Yeah, Nicole.
Number 35.
Number 35. Okay. All right, so number 35 says use synthetic division to determine if all the real zeros in the polynomial lie within the interval -5 to 5 or not. So the theorem that we're going to be using is this one here from last time. So we're going to check for the positive. When we do the synthetic division with the +5, we're looking at for all the numbers at the bottom line to be non-negative, so 0 or bigger. And when we use -5, we're going to look at all the numbers on the bottom line being alternating positive to negative, or non-negative to non-positive. So zeros are okay on the bottom line. So I'm going to check with the -5 first. So I'll set up my synthetic division. I'm going to check as I do that I have all the terms I'm supposed to. So I have degree 3, degree 2, degree 1, degree 0. So we're good there. So let's just fire through that synthetic division there. So that -5 works. We have the alternating signs underneath our synthetic division, so that's a lower bound. We'll do the same thing now with the +5. And all of those are non-negative. So that's my so that is a upper bound. So we can say that all our solutions are between -5 and +5. Does that feel cool? So again, if you knew what to do and what to look at, pretty easy. But if you forgot that theorem, like, oh no, what do I do? Is a normal response here. Can guarantee you'll see this question again on the test. So just as a heads up, you'll see a question just like this again on the test. So you'll want to make sure that you remember how to do that, or at least make a note to yourself to put this kind of thing on your note card. That if you're like, oh, I don't know if I'll remember what to do with that. So that's a freebie for asking a question. Look at that. That's a pretty good deal. Kira. Yes. Get it. Get it? That's an IT joke. Because IT spells it. Anyone else with questions? Or Nicole, if you have another, you're not limited to one. Yeah. Okie dokie. Let's get this show on the road here. So in the last section, what we had done was we had been extending what we learned with our factoring diagram, right? So in section 13.2, we built this nifty factoring tree, but we observed that there was a couple of holes in. Yes, sir. Sure. There are a couple of holes in this factoring tree. right? Like if we didn't have something in the quadratic form, or if we didn't have something that was factorable by grouping, or we had more than 5 terms, we didn't have a method to use. What we did in section 13.3 then was start to build out that method using synthetic division. What we're going to do here in 13.4 is kind of continue to build out that method a little bit more completely. And that'll kind of fill this tree in as well as we can for, for a high school classroom. When you guys are math majors in college and finish that and start grad school, you'll have an opportunity to take a course called computational algebra, which is devoted wholly to, like, how do I solve or factor, these big polynomials, possibly multivariate. Pretty cool. But like, it's a whole branch of mathematics devoted to like this kind of a problem. So we're doing just like the very simplest version of this kind of thing. All right. So continuing on. So we're going to start by introducing another theorem called the fundamental theorem of algebra. Actually, I'll just copy the whole thing in. I abbreviate that as FTA because, well, it's like a lot of words, Grab that. There it is. So what the fundamental theorem of algebra is saying, it actually says 2 things, and as you might have guessed from the name, it's pretty important. What it says is that all polynomials have solutions. And then it tells you that depending on how you're counting the solutions, the number of solutions is equal to the degree. Now, before we had it was at most the degree. Now we have it is equal to the degree. The difference is the first, where it was at most the degree, was the number of real solutions. Here, we have like the total number of solutions. So we have to count, or for the number of solutions to equal the degree, we have to count imaginary solutions also, and multiplicities. So if I get a solution that's used 2 times, that counts as 2 solutions in the solution count here. But as long as you're doing that, you count the multiplicities and you count the imaginaries, the degree is going to also tell you the total number of solutions, which is nice, right? That tells me specifically that when my hunt is done, I know how many answers I should be getting 100% of the time. It's a good deal. In addition to that, we're going to present you guys with 2 other theorems. The first being the irrational conjugates theorem, and the second will be the complex conjugates theorem. So this says a polynomial with rational coefficients. Oops, we should say has rational coefficients if and only if for any 0 of the form a plus square root b, a minus square root b is also a 0. And then that's just saying where for b's that are not perfect squares. So it's basically saying that if you get an irrational solution, those are always going to come in conjugate pairs. You're always going to get 2 of them at a time. So for example, if I have 2 minus the square root of 3 as a solution, I'd also have to get 2 plus square root of 3 as a solution. or if I had negative square root 10 as a solution, I'm guaranteed to get positive square root 10 as a solution. But those are always going to kind of pop in as conjugate pairs. Everybody okay with that? And then we can say the same thing about imaginary solutions. So that's called the complex conjugate theorem. Well, it's almost the same thing. So instead of rational coefficients for the complex conjugates theorem, we have real coefficients. And instead of a plus square root b, we have a plus bi and a minus bi. And the only restriction on b is that it's not 0. That these are imaginary numbers and not just a real number. So again, what this is saying would be that like -2, if -2 plus 5i is a solution, then -2 minus 5i also has to be a solution. Or if 5i over 2 is a solution, then -5i over 2 also has to be a solution. Again, any imaginary solution is going to come in conjugate pairs as well. So again, you're not going to get one imaginary solution only. They're always going to come in pairs, provided that your coefficients are real numbered and not imaginary numbered, which you would never see in a high school classroom. But that's something maybe in your computational algebra class as a grad student, you'd see situations like that where you'd have to consider those. But you're a couple years away from doing that. Where we would likely use these kind of theorems for what type of problems would we do with this? Be a problem like this. Would be to write a polynomial with real coefficients that has the minimum degree necessary and has the zeros 1, -3, and I plus root 2. So we did problems earlier that looked very similar to this, right? So just like before, we're going to start by saying, okay, if those are the zeros, those have to be solutions. And since I want real coefficients, I know that this imaginary solution also has to come with a conjugate pair. So I'm going to add a fourth one. Everybody feel okay there? Now what I'm going to do is I'm going to turn these solutions into polynomials. So I'm just going to move everything onto one side so that they're equal to 0. And the way I think is easiest is when I move that complex number, I'm going to think about subtracting the whole thing. So I'm not like mucking around with a bunch of negative signs. I'll show you later the advantage that we get by thinking about it that way, but I'm going to think about it as just like one number rather than thinking subtract 1 and then subtract like I root 2 separately. I'm just going to subtract the whole thing with a parenthesis around it. Okay, now these are all polynomials that are equal to 0, right? If I multiply all these polynomials together, they're all, or it's still going to equal 0 because they were all equal to 0. Yes, sir. Sure. And now all I'm left to do is to FOIL this thing out. So my suggestion to you is to FOIL out the conjugate pairs, always in the same FOIL. So I'm going to FOIL those first two parentheses and the second two parentheses. I always want to FOIL the conjugates together because it gets neater quicker if you do it that way. If you do the conjugate with a not conjugate, it'll still work, but it gets pretty yucky along the way. So I'm going to go ahead and do that. I'm going to FOIL this first one just kind of quickly in my head. I hope nobody objects to that. The second one, I'm going to FOIL this one by hand also, but I'm going to go a little bit slower and kind of talk through the way I'm thinking about this so that you guys see the way that I am doing this. Because again, I'm going to try to do this in the easiest to keep track of way possible. So I'm going to do like x times x, and then x times that whole parenthesis. Everybody okay? I'm still going to think about that complex number as just one thing. And then to complete my FOIL, I'm going to take that complex number and multiply it by both things in the other. So when I multiply the two complex numbers together, they're both negative signs in front of them. So now it's changing to a plus in front of them. So far, so good. Now I'm going to multiply the rest of this stuff together. So now finally I'm going to distribute through. So I need to remember to take that negative sign in front of my x on my way through when I distribute. And then this, look at these things. Do you notice that I have one plus I root 2 and the other is 1 minus I root 2? That's like a difference of two squares, right? Like a minus b times a plus b. So I know that when I multiply that out, it's just going to be a squared minus b squared. I don't have to FOIL it. You could, you'll get the same result. But, you know, like work hard or work smarter, not harder. You know what I mean? So there my result after I distribute everything through and I do my difference of two squares. If I look, I have I or positive I root 2x and a negative I root 2x. So those guys just cancel each other out. 1 squared is 1. If I do I root 2 squared, well, that's going to be I squared times root 2 squared. Remind me again, what is I squared equal? Negative 1, very good. And square root of 2 squared is 2. So when I simplify 1 minus negative 1 times square root, or times 2, I just get 3, right? All right. So if I combine everything else in here, I have an x squared. I have a negative x, another negative x, so that's negative 2x, and then that plus 3. And now I just need to finish my FOIL. So this is going to be like a triple FOIL. So I'm going to multiply the x squared to everything over there. And then multiply the 2x to everything over there. And then multiply the negative 3 to everything over there. And when I combine these things together, I have a negative 2x cubed and a positive 2x cubed. Those just cancel out. And then I have a 3x squared, a minus 4x squared, a minus 3x squared. Those minus 3 and positive 3x squareds cancel out. So I just have the negative 4x squared. And then I have 6x and 6x, that's 12x, and the minus 9. So there's my polynomial. Has real coefficients. Needed to have 4 solutions, so the minimum degree it has to have is 4, which it does. All the coefficients are real numbered. This satisfies the requirements of the question. So if we go back and we look at this, what was the hardest part about this? It was like the simplifying piece, right? Once we built out the 4 factors, that was pretty easy. Doing all the multiplying them out was kind of tedious. That took the most time. But it was just like foiling over and over and over again. You know what I mean? You just have to go slow and keep track of stuff. But that's all you're really doing there, is like a really elaborate FOIL problem. What do you guys think? It's okay? Meh. All right. Let's now look at some more examples here. Sure. So here it asks us to find all the zeros for this function. So again, if we're going to use the method that we built in section 3 or 13.3, not much has changed, but we can start by observing from the fundamental theorem of algebra that I'm going to have exactly 3 solutions. If I then, okay, where am I going to start my polynomial division? Well, my possible rational zeros are going to be factors of the constant term divided by factors of the leading coefficient, which is just 1, so I don't really need to worry about that. So my factors of 36 are 1, 2, 3, 4, 6, 9, 12, 18, and 36. I think I got them all. Boy, that's a lot of things to guess through. I'm not guessing. I'm going to go look at my graph here and kind of see if I can get a better idea on a starting point. So I'm going to just go ahead and pull up my graphing calculator and type in the equation here. So I have x to the third plus 4x squared plus 9x plus 36. And then I don't know what my window looks like, so I'm just going to do zoom standard after I've typed that in to graph it. And I see just one solution here at -4. And as I look at the graph, is just this x-intercept, the graph is just passing straight through at -4. So you remember back in, where would it have been? I guess it was earlier. Oh, not that day. Yeah. So remember we had this bend, bounce, and straight theorem. So I'm also going to look at the graph and decide which one it, how the graph is passing through that x-intercept. Mine, it looks like it passes straight through, right? It doesn't bounce and hit. It doesn't bend as it goes through. It just kind of whoop, straight through. So that's telling me that I'm only going to be using that 0 the one time. So what are the other two solutions still going to be? They have to be imaginary, right? So you'll never see the imaginary solutions when you look at the graph. The only way to get them are going to be doing the synthetic division process. You won't be able to do like the 0 command on your calculator to get the possible zeros or all the real or the non-real zeros. All right, so -4, I noticed that that's definitely on my list, right? So like here it is, -4. So let's go ahead and do the synthetic division with that. So that's great, right? We got remainder 0. That's what we were expecting. And what that tells me then is that the way to factor this polynomial is x plus 4 times x squared plus 9. So because the -4 gave me remainder 0, I have the x plus 4 as a factor. And then the quotient is going to give me the other factor, right? Now, I know there's no other divisors or real divisors because when I looked at the graph, I saw only the one x-intercept. So I know at this point, to get any more solutions, I'm going to have to deal with the factors separately. So I'm going to set this equal to 0 now. And then solve using the 0 product property. So when I do that, I get -4. Well, like heck, I knew that was going to be an answer anyway. To solve x squared plus 9 equal to 0, I either need to use the quadratic formula, or I could just try to solve this directly, which is what I'm going to do because there's no x term, there's only x squareds and constants. So to do that, I'm just going to subtract 9 from both sides and then square root both sides. When I square root both sides, I get the plus or minus. When I square root a negative number, what do I get? I get an I, right? And then the square root of 9 is 3, so this will be plus or minus 3i. So I have one solution from the -4. I have a second solution for positive 3i, and then a third solution for negative 3i. Those are my three answers, and I know that I found them all because I knew there was only 3 to begin with that I needed to find. Let's do that again, yeah? All right, same idea, it wants all the zeros. So again, I always start, fundamental theorem of algebra tells me that I have 4 solutions here. Then collect my possible rational zeros. So there's the factors of 35 divided by the factors of 8. Then let's go to our graph and take a look there. And we'll just hit graph because we're already on that standard window. Okay, so it's a little too big of a window for me to really have a clear picture of kind of what's going on. But it looks like all the action is happening between -2 and +1 on the x-axis. So I'm just going to change my window to go from -2 to +1 so I can get a closer look at what's going on. Come on, computer. Stop being dumb. No, still fighting with me. Come on now. All right. So I have one solution that's a little bit less than -1, right? And this other solution that looks, well, what does that look like? If that's 0 and that tick mark is 1, that looks like a half to me, right? So let's look over here and what could be that value that's a little bit less than -1. So I could have like, looks like only -5/4 is the only thing that would be close, right? So I'm pretty sure that those have got to be what it is. Which stinks because now I have to do synthetic division with a fraction, but like, it's all right. We can handle that. Of the two fractions, which one would you prefer to start with? Goodness gracious, let's pick that 1/2, right? That's a much easier number to multiply with because it's just like dividing by 2, you know what I mean? So I'll go ahead and set up my synthetic division. So 1/2 of 8 is 4. 1/2 of 22 is -22 is -11. 1/2 of 16 is 8. 1/2 of 70 is 35. Hey, there's my remainder 0, just like I wanted. So we have x minus 1/2 and then times, 8 x cubed minus 22x squared plus 16x plus 70. Now, if I look what I have left over here, that's not quadratic, right? So there's no stopping here. I have to keep dividing. So I am going to have to use that -5/4. Rats! So we'll start the same way. Let's see, that's going to be -10. And then that's going to be +40. And then that's going to be -70. That's great. So now, in addition to the x minus 1/2, we have x plus 5/4. And then, again, these numbers down here, remainder, constant, x squareds. And I noticed that, hey, now I do have a quadratic here. That's lovely. So I will be able to solve that. But if I look at this quadratic a little bit closely, I notice that the coefficients all have a greatest common factor of 8. So let's pull that greatest common factor of 8 out. And now if I'm solving, I don't really need to worry about this. But if I want the factored form of this polynomial, what I would probably do is I'm going to think about 8 as 4 times 5, and I'll multiply the 4 into that one and the 2 into that one. Now, it's not really necessary we do that if we're solving, but if the directions had asked you to factor that, and wanted integer coefficients, you know, it's fine that we did, you know, that we had the fractions in there temporarily. Just means that at some point we're going to be doing some factoring and then can push that factor into the appropriate, you know, into the appropriate other factor to clear the fraction out of there. Okay, so we can set these things now all equal to 0. So again, we get 1/2. That's great. We get negative 5/4. Yep, we knew that. X squared minus 4x plus 7. That's not factorable, right? Because there's not two numbers that multiply to give us 7 and add to give us negative 4. What are we going to have to do instead? Quadratic formula, yes. So negative b plus or minus the square root of b squared minus 4ac all over 2 times a. Now, 4 squared is 16, and then 4 times 7 times 1 is 28. So that's the square root of negative 12 then. Now, because it's negative, we're going to get a I, right? And if I think about 12, that's 4 times 3. The square root of 4 is just 2, but the square root of 3 we can't do anything with. So we have that. And then I can reduce that a little bit if I think about these as 2 fractions with a common denominator of 2. So 4 divided by 2 is just 2, and then like I can reduce that. So again, if I count up my solutions, I have one solution is the 1/2. Second solution is negative 5 over 4. The third solution is 2 plus I root 3, and the fourth solution is 2 minus I root 3. There's my 4 solutions that I was looking for, so I know that I'm finished. So the only additional piece that we got here was we got the fundamental theorem of algebra to tell us exactly how many answers we should be getting. Great. Kind of had that already, though. That wasn't too big of a deal. But we know now that in the case that we get an imaginary solution, how to get those, because you couldn't get them from the graph before. You'd have to have done the synthetic division enough anyways to get to a quadratic that you could use the quadratic formula on or solve directly on to get the imaginary kind of shake out of that. What do you guys think? This is it for chapter 13. This is the last thing that we're going to be doing. So at this point, you guys should be able to finish up the problem set. I think that's going to be 36 to 53. So next class will be the review day. We'll be making our half sheets and such, working on our reviews. We'll talk about the test format and stuff, what to expect. And then I guess Monday of next week will be the test date for chapter 13. What do you guys think? Yeah. At least this should look familiar, right? We all did this last year in Algebra 2, right? So this process should be relatively familiar, should come back to you with a little bit of practice. If you don't feel good about it, make sure that you, in the next few days, comes find me during a CT or something and get a little bit of assistance so that you feel sorted out for the test.